Hello everyone, welcome to the post-contest discussion for Leetcode Weekly 428. I hope all of you had a good contest today and the question today were like pretty good. So let's start with the first question. So the first question was that you're given an 2D array, you're given an 2D array of events. So you're given a 2D array of events and each event was basically represented by an index, that was the index of the event, and a time, the time of the event. And we were given that the events were sorted in increasing order of time, and the time taken to so basically the index indicated that in that event button at that index was pressed, and basically we had to find the time taken, like the button which took minimum time to press, where the time taken to press a button was the difference between the previous time and the current time. Let's go over an example and we'll understand what this means. So this is like the first example was okay. So yeah. So starting with the first question, and the first example basically said that you had second and it might be better. Okay. So the first example said that events were like 1, 2, 2, 5. Then you had 3, 9 and 115. Okay. Yeah. All right. So what does this indicate? Like the first number indicates the index of the button which was pressed. So you had an index over here and a time. So what we are being said is at time equal to 2, we pressed a button at index 1. At time equal to 5, we pressed button at index 2. At time of 3, at time of 9, we press the button at index 3, and at time of 15 we press the button at index 1. So what they're saying is that to press the button at index 1, like what does this event indicate? This event indicates that we pressed the button at index 1, and what was the time it took? Well, it took 2 time, basically like 2 units of time. Then this event indicates that we press the button at index of 2, and it took like the time between the current time and the previous time, the difference between these two, that is 5 minus 2 equal to 3 units of time. Then to press the button at index of 3, we took 9 minus 5, which is 4 units of time. And to press the button at index 1, this fourth event, we took 15 minus 9, which is 6 units of time. And what we have to calculate is what is the minimum amount of time that any button has taken, what is the index of that button. And if there are any clashes, then we'll have to return the button with minimum index. So over here, as you can see, the button with like the minimum amount of time is 2. Okay. And so if you just look at it, like this was our button index, this was the time that it was pressed, and this was the amount of time taken. Then the button at index 1 took was pressed at 2, and it took 2 amount of time. The button at index 2 was pressed at 5, the fifth minute, and it took 5 minus 2, that is 3 minutes to press. button at index 3 was pressed at 9th minute. Let's just say minute rather than units of time, it's easier. And it took the 9 minus 5, that is 4 units of time. And button at index 1 was pressed at the 15th minute, and it took 9 minus 15, that is 6 minutes or 6 units of time. So in this case, like the minimum amount of time you have is 2. So the like corresponding index for this 2 is 1. So your answer would be 1. That is the minimum 1 is the button which had the minimum press time to press. And if we move on to the second test case for 2 was like kind of similar. So over here you said that the button with index 10 was pressed first at time 5. Then you press the button at index 1. I think I have messed up a bit. Yeah. Then you press the button 1 at time 7. Okay, sorry. We had to calculate the button with the longest period of time. So it won't be 2 over here. It would be 6. Sorry about that. So button with index 1 was pressed at 7. So it took 5 minutes to press button 10 because it was the first button to be pressed. For button 1, you had 5 minus 7, that is 2 minutes to press this button. So the maximum amount of time was taken by this button, that is 5. So, and the corresponding index over here is 10. Now, one more thing that could happen, but that wasn't covered in sample test cases, was you could have multiple buttons that have the same time required to press. For example, you could press button 2 at time equal to 2. Then you could press button 1 at time equal to 4. Then you could again press button say 3 at time equal to 6. Now, if you see, the first button takes time 2 to press. The second button also takes 4 minus 2, that is 2 to press. Then the third button takes 4 minus 6, that is time 2 to press. Now, in this case, according to question, what you have to do is, since all these three are like equal, all of their indices are valid indices, like all three of them are maximum time taken to press a button. So what you have to basically do is you have to take the minimum of the corresponding indices. So the minimum over here is 1. So the answer would be 1 in this case. That was like about this question. Just a second. And moving on to the implementation of this question, like we maintain a longest time that any button has taken up to now to basically press the button, and we also maintain what that button is for whom the longest time was taken. Then we also have the previous time. So for initially the previous time would be 0. Like I think this is something from the previous code. So then for each of the button, what you do is you basically start from I equal to 1 and iterate up to like the end of the array. So I equal to 1 indicates the second button. Now, what is the time required to press this button? Well, it is at which time was this button pressed minus at which time was the previous button pressed. That is the time required to press the current button, and this is your current button. Now, if the current button took like more time than the longest time up to now, then we reset the longest time and say that this is the button which took the longest time to press. And if the time is equal to the longest time, then we try to see if, okay, the longest button hasn't been discovered, -1, or if the current button has an index lower than the longest button, then we'll update the longest button. And finally, we just return the longest button. So, yeah. And let's just say that that was about this question. So I'll just dry run once through the first test case. And if you have any doubts, please do ask in the comment section. Like, So this is your index, this is your time, and you basically start with 1, 2, 2, 5. You have 3, 9, and 115. Initially, your what I should say, like this is the longest time, and this is the button which achieved that longest time. And also, you would have one more, like the amount of time taken by this button to press. Uh, let's just say time. So initially, you would have the longest time equal to 2 and the button equal to 1. So that's what we do in this first condition over here. And moving forward, what we do is we calculate this, like 5 minus 2 is 3. Is 3 greater than 2? Yes, it's greater than 2. So we set like the longest time has to be updated. Well, it's 3 now. And the button has to be updated too. So it's 2 now. Then from 5 to 9, the amount of time taken is 4. Is 4 greater than 3? Yes. Then the longest time has to be updated to 4. And the button has to be updated to like what is the corresponding button, that is 3. And 9 to 15 is 6. Again, the longest time has to be updated to 6 and the index has to be updated to 1. Now let's just say that rather than being 1, this was something like 5. And if after 15 you have 15 plus 6, 21, and this was 1, then your longest your time taken to press this button would be 6, and now 6 and 6 are equal, so your longest time would remain the same, but your index would be updated to minimum of what it already is and what is the corresponding index over here, so it would have been 1. That's how you solve our first question. And so okay, I don't think what is the typecasted event dot since. Okay, so the reason why I have typecasted event dot size into int is that in C++ you get a warning when comparing an integer with a long, and size is by default given in long type. So that's why like I have typecasted it to avoid those warnings. And I think someone has shared their code. Okay. Right. I think we can move to the next question. Oh, hello. And this was about the second problem. So in the second problem, actually, we were given. So if you look at the second problem of today's Leetcode Weekly, in our previous discussion, like we considered about the doubt about the cycles, and if you actually just go through the question once more, in the question we're basically given that on day one, you can convert your basically a pair of conversion rates. You can convert a start currency to a target currency at a fixed rate on day one. And on day two, you can convert a start currency to target currency with some other fixed rates. So like there was one question, like the question said that there won't be any cycles in the uh, there won't be any cycles or contradictions in the given problem. So basically, we were given that on the first day, you could say that you could convert EUR to USD with a conversion rate of 2.0, and you could convert USD to JPY with a conversion rate of 3.0. And vice versa, you could also convert JPY to USD with a conversion rate of 1 by 3, and over here, once again with a conversion rate of 1 by 2. Now, this means that effectively you could convert EUR to JPY with conversion rate of 6.0. All right. Now, what happens if there are two ways to reach JPY? Well, you could reach EUR to USD and then USD to JPY. Well, in that case, like this is 2 and this is 3. And say you could reach from EUR to INR. and then INR to JPY with a say like 3 and 4. You could convert euro to JPY with a conversion rate of 12, and you could also convert euro to JPY with a conversion rate of 6. Now, in a normal directed graph, this doesn't lead to any cycles, but in this case, this would lead to a cycle because each of the conversion can also be traversed in reverse. So what we can do is we can traverse basically this INR conversion. We start with 1.0. We traverse this INR conversion. We have 3.0 over here. We have 4.0 conversion rate. We get 4 is a conversion rate of 12. And we can traverse both of these edges in reverse. Like these are the 2.0 and 3.0 edges. What we can do is we can traverse this edge in reverse. We can say that I am going to convert my JPY to USD. 3 JPY give me 1 USD. So that will be like 12 by 3, 4, and 2 USD give me 1 EUR. So 4 by 2, 2. Like this leads to a cycle, and we could basically go on repeating this cycle and get an infinite number of euros on the first day itself. So such a cycle would not be valid. And basically, since such a cycle would not be valid, we will just have rates in the form of euro can be converted to USD, then JPY, and just so on and so forth. And at most, like what would happen is we could have branches moving forward. This won't lead to cycles, but anytime like we have something of this form, that would indeed lead to cycles. So basically for this problem, what we do is, first thing that we do is we determine the max amount of a currency that we can have on day one. And to do that, we start a DFS starting a DFS or a BFS starting on our initial node. Then we visit all of its neighbors and say that like we use this conversion rate. So initial this is 1.0. We use this conversion rate R1, R2 to get there. What will be there? Basically the amount of money on day one. Then we get these things like this is R3 and R4. Then just what would be the maximum amount at the end of day one for this currency, then what would be for this currency, and we just iterate so on and so forth until like we get for each node what is the maximum amount at end of day one for this currency. So if we were to go through our current example, like you could convert euro to USD and you could convert USD to JPY. Let's just say there was also INR over here or CHF. Then what we would do is we would start at 1.0. We'll have a conversion rate of 2. Then that gives us 2 USD. This has conversion rate of 3 and say this has 4. Then 3 to the 6. That would give us 6 JPY at the end. And that would give us 4 to the 8 INR at the end. And on the second day, what we do is on the day, what we want is what is the maximum conversion rate that I can have from my currency to my initial currency. So what we are doing is we take our initial currency, we convert it to some other currency X on day one, and our first DFS gives us like what is the maximum value of this X can be. Then on day two, we take this X and again we have a conversion rate of Y and convert it back to X into Y euros, EURs. EUR is our initial currency. Now, the first DFS basically allows us to maximize this X value. And the value of X has been maximized on day one. And now we want to maximize this value of Y, that is the conversion rate from this currency to my euro. EUR, the initial currency. And to do that, what we do is, well, what is Y? My Y is, say, I start at JPY according to my problem statement. Then I go to CHF. Then we go to USD. And finally, all after all this, we get to our initial currency EUR. Well, this is the product of rates of all these things. So this is R1 into R2 into R3, in test cases 3 into 4 into 4, or yeah, I guess it is 4 into 5 into 6. So in our test case is 4 into 5 into 6. So basically what we want to do is we want to find for each of the currency what is the like minimum value that it like what is the maximum rate, like what is its conversion rate with respect to this the initial currency. Now one thing that we could of course do is like we could just go over all the currencies and basically update all of their neighbors and just start a BFS from each of these currencies. But until we reach our initial currency euro. But a simpler way would be that we reverse our edges. Like when I reverse my edge, what I'm saying is that if I can convert uh, 1 JPY to 4 euros, then initially like that would indicate an edge of from 4 from EUR JPY to EUR. But now what I'm saying is I'll indicate that as an edge from EUR to JPY with a 4. That basically means that there is if there's a path from EUR to JPY with a total multiplication of all rates X, then that means that I can convert 1 unit of JPY into X units of EUR. Then again again what we could do is we could just start a BFS from our initial node. We could get the total effective rates for each of these nodes. Now an effective rate of R, that is basically product of all these rates from path of initial to this node, then a total effective rate of R implies that if I have X units of this currency, say JPY, and I have an effective rate of R over here in this reverse graph, then basically what I can do is I can take this R and I can traverse this path in reverse and like traverse this path in this direction and basically convert my X units of this currency into X dot X into R units of my initial currency. So basically my complete the total number of currency that I would have after converting it to X on day one and then once again converting it to initial currency on day two would be X into R, where R is the total effective rate on day two. And moving to the code for this. So first we get our two adjacency lists and we construct our adjacency matrix for day one. Well, adjacency matrix for day one is constructed in the order that if you can go from one node to another node, then you can with the rate of R, then you can convert 1 unit of start to R units of target. And we construct our adjacency list for day two in reverse. So this implies that you can convert R units of target into start basically in the reverse of day two. So an edge from start target A to B implies that you can convert 1 unit of B into R units of A. Then we go on to calculate the maximum amount that you could have on day one. Well, since there's no cycles in the graphs, so what we have to do is a basic BFS or even a DFS would do. So we start with our initial currency. It would initially have like exactly one amount on day one. We push that into queue. This is a normal BFS. We take the first currency in our the currency at the front of our queue, pop it, then look at all its neighbors, look at the rate that it's connected to its neighbors. Then we see like if that neighbor is already visited, like over here we are doing it by since this is going to be 0. So we'll just update the value of that neighbor to the amount of current value that I have for the current currency into the conversion rate. That would be the value of my neighboring currency, and we just push in queue and continue our BFS. We do something similar for our second graph, and that would allow us to basically for our second graph, like that would basically allow us to calculate our maximum conversion rate. And like this would be the maximum distance from the start node in our reverse graph that would be our maximum conversion rate from that currency to the initial currency, and this is once again BFS. Now in here what we do is initially we input our initial currency which has a conversion rate of 1. Then each time we encounter or like okay we are processing this currency, what we do is okay this is the maximum conversion rate we have on day 2. Like on day 2 I can convert 1 unit of this currency back to these many units of initial currency, and this is like the maximum amount I could get of this currency on day 1. So what we do is we take the maximum amount of this currency on day 1, and we apply the conversion rate on day 2 and see how many uh, can we get on day 2 by converting all currency into this currency and then once again back into our initial currency, and then we just continue our normal BFS, and finally we just return our result. Our result is initially 0, and we just take maximum of all the possible currency conversions. Like any currency conversion would occur in, you have initial currency, then you convert it to some currency X on day 1, then you take this X and you convert it back to your initial currency on day 2. So this is the simulation of the whole process. And why wouldn't it be like in a sense like you convert initial currency into X into Y and then you can once again convert into both of these. So why wouldn't there be two currencies? Well, it depends on the effective rate. So if the effective conversion rate, basically what we gain after conversion is if I have 1 unit and my effective conversion rate for R is for X is R, then I get R units on day 1. And if my effective conversion rate from like R to 1 is R2 on day 2, I get like if this is R1 and this is R2, then I get R1 into R2. And what we want to achieve is we want to basically maximize this amount. Now, each currency will have both R1, that is effective conversion rate from 1 to this currency on day 1, and R2, that is effective conversion rate from this currency to initial currency on day 2. And if one of the currencies and one of them will be maximum, so we'll just be like kind of considering maximum, because for each unit that you put into that currency you're getting the maximum benefit, so it won't like make sense to have some other currency that has lesser conversion rate. In that case our answer would end up being suboptimal. So yes, that was about the second problem, and just that there won't be any cycles in here, and even something that usually doesn't qualify as a cycle in a directed graph would be a cycle here. So if we had something like 2, 3, 4, and 5, this would lead to cycle because we could traverse our edges in reverse with a weight of one by conversion rate. So we would have a weight of 1/4 and 1/5 over here. So if I go from here to here, that would have a conversion rate of 6. Basically, like the effective conversion rate from this node to this node with this path and with this path, this is 20 and this is 6. So what we could do is we could traverse this edge in reverse. By traversing this upper edge in reverse gives us like traversing this edge gives us a rate of 20, and traversing upper edge in reverse gives us an effective conversion rate of 1/6. So basically what we end up having is we end up having that we can convert euro to itself, like basically we can multiply euro to itself 20/6 into 20/6, and that would imply that on day 1 itself you could make euro go up to infinite by just by just traversing this cycle over and over and over and over. So such graphs like won't be allowed by the problem constraints. And yeah, that was the problem. Thank you. Problem. The third problem says that count beautiful splits in an array. And what they had given us was an array nums. And we had to split this array into 3 non-empty subarrays, nums1, nums2, and nums3. And nums could be formed by concatenating all these 3 arrays. And we had to ensure this one condition that either nums1 is a prefix of nums2 or nums2 is a prefix of nums3. Now, and we have to return how many ways can you make this split. So in how many ways can you split our array into three continuous uh, non-empty sub-arrays, such that one of them is like one nums1 is a subsequence of the next, or nums2 is a subsequence of the next array. So if you go, if you just look at our sample test case, so the array given to us was 1 1 2 1, and if we look at it, this is all right, 1 1 2 1. What we can do is, so for nums1, for nums2, and for nums3. For nums1, we can have 1 as our array. It has to be non-empty, so we cannot have an empty array. For nums2, like this is the remaining array for nums2, so we can have 1 and 2 1 over here, or we can also have two, sorry, not 2 1, 1 and 2 and 1 over here. So we could split our array in this format or this format. Now notice that this the nums is a prefix of this guy. So what does it mean by being the prefix? So I can take any prefix of nums2, I can take some prefix of nums2, and that is going to equal to nums1. So in both of these cases, that condition is satisfied. So these two are like valid splits. What's the next split that I can do? I can have 1 1 in my nums1, then I can have 2 in my nums2, and I will compulsory they have 1 in my last array, because none of the arrays can be empty. In this case, is nums1 a prefix of nums2? No, it's not. Like the first element of nums1 is 1 and the first element over here is 2. So the first element itself doesn't match. Now is nums2 a prefix of nums3? No, again, because these two elements basically don't equal to each other. And so this is not a valid split, but these two are valid split. So our answer is 2. So we have 2 valid splits. And what we have to find is how many such valid splits do we have. So if we and our nums dot length is like the size of our array is less than equal to 5,000. So which is 5 times 10 raised to power 3. So what you could do is you start iterating, like say this is your nums array. Okay. You assign some part to nums1. Then you assign some part to nums2. And finally, you assign some part to nums3. Let's just say this starts at I and this starts at j, and this will obviously start at 0. Then your each split can be represented as like you start your nums1 array at 0, you start your nums2 array at I, and you start your nums3 array at j, and 0 will basically have to be less than I, and this has to be less than j, because each array has to have at least one element. What you have to do is you basically have to, one of the two condition has to be satisfied, that is this nums1 like this nums1 is a prefix of nums2. What happens when nums1 is a prefix of nums2? Well, some part, if this is nums1, then the first part of nums2 is equal to nums1. So if this is say length L, then the first L part of nums2 is equal to this guy. And either this or the other condition, which is that nums1 and nums2 may not be equal. Nums1 and nums2 may not be equal, but you could have like nums2 and nums3, like nums2 can be a prefix of nums3. So one of these conditions has to hold for this. And what we can do is right now, what we can do is we can iterate over all the different partitions. So there are total big of n squared, there will be total of big of n squared possible partitions. Why? Because you could iterate from I equal to like 1 to n minus 2, and for each of these I you can iterate from I plus 1 till n minus 1, and you have these many partitions. Now for each partition you basically have to check if that partition is valid. And the problem was, how do you check that this partition is valid in O of 1, or in a very small time complexity? Now, before that, let's just say that we try to solve a simpler problem. Rather than two partitions, let's consider what happens when you try to make only single partition. Okay, so consider an array like 1, 1, and 2, 2, and 1, 2. All right. Okay, like this is right. So consider what happens when you try to consist only one partition. So we'll deal with two partitions later on. Consider what happens when you just consider one partition. Okay, what happens when I have a partition over here? What I want to do is I want to check if I have a prefix of length 1. Does this one and this one match? Like, do these two ones match? Then I can, the next partition I could have is this partition 2, 1, 2. Does this prefix and this array, so basically like this part of my array, a prefix of 2 in my array, and this guy like prefix starting at index 2 and of length 2, do these two match? If they do, then this is a valid partition. If they do over here, then even this is a valid partition. And I'll just continue so on, and this will be like my next partition. And what I have to do is I have to check if this prefix and this prefix match. And finally, like after this, my prefix, like the first array would have 4 elements and my next array would have only 2 elements. So in no case can this first array be a prefix of the second array. So basically, for if you consider only one partition, you're basically checking if I am partitioning. Yes. So if I am partitioning starting at I, okay, and considering zero based indexing, so I have 0, 1, 2 all the way up to I. If I'm partitioning starting at I, so my ith element is the first element in my second array. Is my array from I to I plus I? Why? Because like we need to consider prefix of length I. This prefix is of length I. Is this equal to my array starting from 0 till I minus 1? And there are many ways to check this. So basically what we are doing over here is we have this I, and we want to check if this thing with the length of I is equal to this thing over here with the length of I. Okay. And if we can check this thing in like big O of 1 time complexity or something, we could solve the answer. We could get the answer for exactly one partition in big O of n time complexity by iterating once. Now the question is, how do we check if this I, this part of the array, is equal to this part of the array? There are many ways. One of them would be using hash functions, like hashing these arrays and maintaining rolling hashes. This is something covered in TLE level 3. I think it's at the end of level 3, like near end of level 3. And but there's one more way to deal with this, that is string matching algorithms. So what is string matching algorithms? Basically, they allow you to say that you have a pattern, you have a pattern string, say AA, and you have a text string, say ABC, AA, DAA. Then what they basically allow you to do is you can take this pattern string and see where exactly does my pattern occur in my text string. And you can kind of use these algorithms to check if your prefix lies somewhere in your the remaining rest of the array. Now, how do you use these? So what we'll use over here is Z algo. So with Z algorithm, what it does is that, any doubts up to this point?
Excuse me, sir.
Yes,
Sir, I want to ask that can we do it using prefix sum approach here?
using the prefix sum, like the hashing approach.
Yes, sir. Something like that, sir. I mean to say.
All right, we can do it using the hashing approach. So in the hashing approach, like basically what you do in the hashing approach is uh, you have, let's just say, like 1 2 3 and then 1 2 3, and so you define the hash of an array. So let's just say you have this array 1 2 3, and you define the hash of this array. Now what is the hash of this array? The hash of this array would be, what would be my array be if I like multiply these numbers by, so one is multiplied by what is the power of this. Like basically what you do is you associate each number. You decide, first thing you decide is you decide on a base number. Over here, let's just say that our base is 10. Then what you do is you basically associate a base power of base with each of the number. So 3 will be associated with 10 raised power 0, 2 would be associated with say 10 raised power 1, and 1 would be associated with 10 raised power 2. So basically like your hash of array like 1, 2, 3, 4 would look something uh, like, let's not do it in reverse. I'll just do it in a normal way. So 1 into 10 raised power 0 plus 2 into 10 raised power 1 plus 3 into 10 raised power 2 plus 4 into 10 raised power 3 modulo some number mod. Okay, and for now let's just say this modulo is usually a prime number. So let's just say that for now you're just considering 7. Then this would be like 1 plus 2 is 20, 300 and 4000, and that modulo 7 would give you some number. So this would be like, I guess, modulo 7, this would be 7 6 plus uh, 3 is a 9, that 7 is once again 6 plus 9 is 2, and so 6, so this would be 3, and like total overall modulo 7, this answer would be 2. So basically like this would allow you to calculate the hash of an subarray, and the idea for hashing the subarray is that you maintain rolling hashes. Like what you do is we start with let's just say we start with I equal to, so we start with the first partition. So this is my nums1, I say that this is my nums1, this is the start of my nums2, and this is the start of my nums3. And what we do is initially I have a certain hash 1 for nums1, which is 1. Then I have certain hash 2 for my nums2, which is initially 2. And for nums3, I have another hash function that is 3, 1, 2, and 3. So initially we calculate all of these hash functions, and to check if basically this nums1 is like equal to the prefix of this length in the second subarray, you check if these two hashes are equal. And all right, so not 3 hashes, you would need to maintain 4 hashes. What you would need to do is you would need to maintain 4 hashes. So this is like the first hash would be like the hash of the nums1 array. Then the second hash would be the hash of prefix in the nums2 array, which has a length equal to the nums1 array. then we need to maintain an hash of the overall nums2 array and also the length of prefix in the nums3 array, which has a length equal to the nums2 array. And what we do is in each iteration we update these hashes. So like what happens is in the nums1 hash, let's just say initially you have some hash h, and for the prefix in the nums2 you have some hash h2. If you compare these two hashes, if these two hashes are equal, then you have like nums1 as a prefix of nums2, and then you have a valid pair, then you can increment your answer. If this does not hold, then what you could do is you could compare the hash of nums2, say h3, and compare it with prefix of nums3 hash. And if this two matches, if this doesn't match and these two matches, even then it's valid and we can increment our answer. Now the question is, how do we update our hashes? Now, if you have hash for this complete arrangement and we want to add one number over here, so what we do in that case is, what is the hash of this array? Okay, let's consider we have numbers 1, 2, 3, and we have hash for this 3, and we want to add the number 4. And to do that, what we do is, our current hash is 1 into like 10 raised to power 0 plus base raised to power 0. So I'm just considering not even 10, I guess. 7 raised to power 0, that would be our base. 1 into 7 raised to power 1 base, and 1 raised to power 1 into 7 raised to power 2. So I think we consider base as something else, but yeah, like overall it would be hash into something of our base. Now what we want to do is we want to add this next number into our hash, and our updated hash would look like 1 into like base raised to power 0 plus 2 into base raised to power 1 plus 3 into base raised to power 2, and 4 would be added with base raised to power 3, right? Now if you actually look at this thing, this complete thing is our previous hash, so this is h dash, h plus, that is our previous hash, plus 4 into base raised to power 3. So basically, like what this would do is to add 4 into your answer, like to add 4 into your hash, what you have to do is we have to consider the current length of our array, and we have to basically add, like multiply 4 by base raised to power the length of our array and add that into our hash and take modulo. O of n square, n is 1000. Sir, this fails. Okay. I think I think the code that you shared is O of n cube, not O of n square. So that would fail because you have three loops. All right. And basically that would be how you would add a new number into your hash. So if you have this array with certain hash h and you want to add, and this has a length l, and you want to add a new number x, your updated hash would be h plus this new number x into your base raised to power l. And what do you do if you want to remove an element from your hash? So let's just say you have a hash for this array, which is h, and you want to remove this element. Well, your current hash would look something like h into base raised to power 0 plus the next element into base raised to power 1, and so on and so forth. And your updated hash, in that this element would be removed and this element would come over here. You will have base raised to power 0 here, and that would be like continue, so on and so forth. Now you could actually see that your h can be represented as x plus h dash into base. So your new hash can be kind of calculated using this thing. Now we can basically in modular arithmetic you could basically divide your h minus x by a base, and that would imply multiplying by the inverse of the base. So basically what you could do is you can start from I equal to 1. Like first thing you do is you maintain three hashes, let's just say h0, h1, h2 and h3. Then initially h0 will indicate the first element, h1 will indicate the element over here, h2 will also be this guy, and h3 will be the first element in the third subarray. And then you start from I equal to 1 till n minus 2 and j equal to I plus 1 to n minus 1. And basically like for each I what you do is, for each I what you're doing is you have this I and you're answering, like you're adding I minus 1 to the hash 0, that is the hash of the nums1 array, and you check if the nums2 array has a length enough to accommodate a new element, and then if it has, then you try to add the new element into h1. Also when you like kind of increment j, then you also need to add a new element into h2 and try to see if you could accommodate a new element into h3. And yeah, I guess like that would be the overall idea for the hash function. There's like I don't really have the code for it right now. So the code that I did was using Z function. And so what you have in Z algorithm is that you have this element Z of I for an array nums, but Z of I says that what is the maximum length such that array starting from I is equal to prefix of I. Like what this says is, for example, if you have this array 1, 2, 3, and you have this array 1, 2, 3. Okay, the first element isn't considered, so let's just set it to 0. The second element, what is the maximum length such that the subarray starting here is equal to prefix? Well, it's 2 equal to 1, no, so I can't have any prefix starting
कर
here.
लेंगे मामा अच्छी मैंने दोनों कारण से उनको मान तो पिछले लोग तो पैसा कमा के उनको बहुत बहुत खुद को ये समझते हैं लोग
So for 1, 2, 3, basically if you look at 1, what is the maximum prefix starting, what is the maximum subarray starting at 1, which also equals to this prefix? And that would be like, is 1 equal to 1? Okay, it is. So like one subarray is 1. So we have a prefix that equals to this thing. For 2, we have a prefix that equals to 1, 2. For 3, we have a prefix that equals to 1, 2, 3. So we can have 3, like z function would equal to 3 over here, and 0 once again for all of these guys. And yeah, I mean like basically like this is the whole function to calculate the z function. And once you have the z function, what z function says is that your z of I means that if you are at the ith element and if you are at this prefix, and the ith element has a z of I value of z of I, this basically says that my array from starting from I, or and with the length of z of I, this array is equal to my prefix array. All right, so basically what I can do is I can have my array and say that my ith element has a length of has a z of I value of 2. This implies that as long as my nums2 has a length less than equal to 2, this is a valid partition, because if my nums has a length less than equal to 2, my z function says that any array starting at I and with a length less than equal to 2 is equal to the prefix starting at the start of the array and length equal to that length. So this basically ensures that if my nums of I, if this thing is like 2 or 1, and I has a value of z of I equal to 2, then this basically ensures that this prefix is equal to a similar length of subarray starting from I. So that's how we could use z function to basically calculate these things. And yeah, like this is what I've done in simple splits. So what we do is we start from I equal to 1 till n minus 1. Then we start from j equal to I plus 1. And for each array, what we do is this condition, basically what this condition says is, yeah, right. What this says is my z of I, like, is my z of I greater than equal to I? What does z of I greater than equal to I imply? Well, my z of I being greater than equal to I implies that I have I elements over here, all right? And starting from this element, I can have z of I, I can have any size of a subarray of length z of I, and its any of its prefix will equal to prefix over here. So if my z of I has a length of at least I, then I can just start from here, cut off an array of length I, and both of these arrays would be equal. So basically my condition that nums1 has to be a prefix of nums2 is satisfied. Also, one more condition that has to hold is that when I start from I, my j must not be like my j must not be less than I. So basically, if I want to consider this prefix of length 3 and my I is here, and after like just two places I have j, then if I start considering a prefix of size 3, then this would intersect with nums3. So these are the like two conditions: j greater than equal to I plus I and z of I greater than equal to I. This will check if nums1 is a prefix of nums2. And the second condition would be like what you do for the second case is basically you create a remaining nums array, and we do something that's very similar for the second array, that we basically check if uh, the maximum prefix starting from here, like what we do for the second array is, okay, my first array is not equal, now I have second array, this is my remaining array, all right, and I have my j over here. I calculate a z function differently for this array, and then I see, okay, what is my z of j? If this z of j is greater than or equal to this length L, then I have this nums2 as a prefix in my nums3 array, basically the first L element starting from j. And so what we have over here is basically, is nums1 a prefix of nums2, or is nums2 a prefix of nums3? If it is, we do plus plus arrays. We could similarly do it with Rabin-Karp algorithm, like rolling hashes, and that would be fine too. And yeah, so this was the final question. The final question said that you are given a string S. The final question said that you are given a string S, and a string is called good if all the characters in that string occur the same number of times. And you could perform certain operations. In one operation, you could delete an character from S, or you could insert a character from S, or you could change a character to the next character. But like basically, you could change A to B, B to C, or C to D, but you couldn't change Z to A. So like there was no reverse H at the end of the characters. And what we had to do is we had to return the minimum number of operations that are required to make the string given string as good. So we're given in the sample test case, we were given A, C, A, B. And over here, as you can see, like A has a frequency of 2, C has frequency of 1, and B, you just have one character. What you could do is we could do one operation, delete an A, and we would have C, A, B. And so this total took one operation, so our answer would be 1. And in the next test case, you had W, D, D, W. So you have WDDW, and this is good by default because you have two Ds and two Ws. So this is good by default. And finally you had, yeah, this is like 3A and BC. How do you deal with this? Well, what you could do is you could convert one A to a B. You end up with AABBC, and you could delete the last C. You end up with AAB, which is a good because we have two A's and two B's. So all of them are uh, like this is a valid string. So you needed two operations. So your answer is 2, and it's 2 over here. Okay, and that was the second problem, the last problem. And what we have to do over here is we have to minimize the number of moves that we require to make it good. Now the first observation is that order doesn't matter over here. Like the order of characters doesn't matter. Only frequency matters. Okay. So the order of characters doesn't matter, only frequency matters. So for example, rather than considering the string AABBC, what I can have is I have character A with frequency of 3. I can have character B with frequency of 1. I can have character C with a frequency of 1. All right. Now, what does a good string look in terms of frequency? Well, in terms of frequency, if you look at the final string, that is AA and BB, it has two A's. It has two A's. It has, sorry, I wrote it into this. It has two A's, it has two B's, and it has 0 C's. Okay. So basically, if you look at a good string, it will be composed of like for A, you could have 0, for B, you could have 0. But if for C, if you had 3, then D could either be 0 or 3, and all of the elements could either be like 0 or one of these things. So basically, a good string frequency is either 0, the frequency of each character is either 0 or some constant. So over here that constant was 2, and over here that constant is, we have assumed it to be 3. Now, what are our operations in terms of the frequency array? So we were given operations in on string. Now, what are our operations in frequency array? And this frequency array will have a size of 26 because it's given that there are exactly like it will correspond to exactly the lowercase Latin alphabets, which are 26 A to Z. So what are operations in terms of frequency? Now the operation says that one, you could insert a character. Well, if you insert a character, that will correspond to incrementing the frequency of that character, right? Then you could delete a character. What would deleting a character do? Well, if you delete a character, that would correspond to decrementing the frequency of that particular character. And finally, you could change a character to its next. So if you can change A to B or B to C, that will be like you decrement the frequency of some character and increment the frequency of the next character. We'll say that this is CH plus 1 using zero-based indexing. So you have these three operations. Basically, what you can do is if you have an array of size of form say 210, you can increment a character. So you can increment 2 and convert it to 220. You could decrement a character, say decrement 1 and convert it to 200, or you could decrement one character and increment its next character. So decrement 2, that becomes 1, increment 1, that becomes 0, and you have the 0 as finally. And what you have to do is you have to find minimum operations to make like either each element to make all like to make either like all elements are 0 or some constant, like some constant key, some constant. Let's just call it x. Okay. Now we have to find the minimum operations to basically convert the complete array into zeros, or like each element can be either 0 or this some constant that we have fixed x. Now what we can do is it's a very difficult thing to just let x float and say that how do I convert my array into some x. Rather than that, what can be the maximum value of frequency in our array? Well, in the worst case, like I can have my complete array of size n as having all the same elements. So my maximum frequency can be n. My minimum frequency can be 0. Like basically, in the worst case, I don't have any character, so my minimum frequency will be 0. And in any optimal scenario, my x is going to be like greater than equal to 0 and less than equal to n. What I can do is I can iterate over all x and try to fix x and see what is the minimum number of operations to make all elements 0 or x. Okay, I'll start with whatever frequency array I have. I'll fix an x. X can be between 0 to n, so I can have any x. And I'll try to see what is the minimum number of operations that I need to convert my array into either 0 or x. And how, okay, now how do we do this thing? Now, notice that what we are doing over here is you start with a frequency array and say your x is equal to 2. Now there can be three things. One, that the element in your frequency array is less than x, or it's greater than x, or it may be 0, and let's just say 0, 0, and something like 2. Okay. Now the first two, if we only had first two operations, like what we have to do is very simple. If we just had like the only two operations for now, if we just ignore the third operation, if we had only the first two operations, what we would have to do would be very simple. Like I have to bring x like 1 either to 0 or to 2. Like it takes one more to move it to here, one more to move it to here. Like I can do any of them, and this would contribute 1 to my answer. Then I could move 4 to 2 with basically like I could move 4 to 2, which would take me 2 moves, or I could move 4 to 0, which would take me 2 moves, and that would cost you like 2. Then 0, 0 would remain like itself because we aren't considering zeros, and 2 is already 2, so we don't really need to make any moves. So basically what we could do, if there were only two operations, we could try to change every element to 0 by decrementing it, or to x by either incrementing or decrementing it, and this would cost us like absolute value of x minus frequency of I number of operations, and this would cost us frequency of I, absolute value of frequency of I operations, and we could take minimum of these things, and the sum of them would be our answer if there was no third operations. Now there is a third type of operation that basically allows us to take two adjacent elements and say this is 3 and this is 1, and we can basically transfer one element from here to here. This would be converted to 2 to 2, 2 and 2. Now notice one thing, if I do this operation like consecutively two times, like not on same element. So for example, if I have one, not one, 4, 1 and 1, and if I do this operation once, then my array would become 3, 2 and 1. And if I do this operation one more time over here, then my array would become like 3, 1, 2. Effectively, what I have done is I have used two operations to move an element from this 4 to this one. Okay, but this is not an like efficient way to move this to make this movement. Rather, what I could have done is like over here, this doesn't give me any advantage. What I could have done is for this 4, 1, 1, I could have just decremented my 4. That would have been 3, 1, 1. Then I could have incremented my 1. that would have been 3, 1, 2. So both of these things take similar number of operations. Now, if rather than this, I wanted to move an element from 4 to this one, moving it would take 3 moves because I would have to move from 4 to 1, then from this one to this one, from this one to this one. So this would have taken 3 moves, but using only the 2 operations, I could just move it like I could decrement the 4, then I could increment the 1. So what I'm trying to say over here is the operation of moving from one element to the next element from 4 to 1, this only makes sense, like this is only optimal when you are doing it on adjacent element. So there won't be, in an optimal solution, there won't be there won't be any moves where you basically do an operation of moving from this element to this element, then once again moving from this element to this element, and then once again moving from this element to this element. This won't exist in an optimal solution. At most you could have these type of movements, and even in that case you could replace it by two increment and decrement operations, like one increment and one decrement operation. So we only need to consider the to construct our solution, we only need to consider the third operation being done on adjacent elements. All right. Now, so the third operation can only be done on adjacent elements, and now we know that we have also fixed our x. So we want to make each of our element to x. That will have a cost of either absolute value of the like current frequency minus x, or the absolute value of the current frequency. Basically, make it 0 or make it x. What else can we do? Well, I have this f of I and I have this f of I minus 1. Now there can be 2-3 conditions. The first is I ignore this f of I minus 1. I just ignore whatever it is and I convert my f of I to basically either 0 or x. This will have a cost of f of I and this will have a cost of absolute value of x minus f of I. So I just ignore f of I minus 1 and I proceed with one of these paths. That's one thing I can do. One more thing that I could do is I consider my f of I minus 1 and the rest of array is basically ignored. And in that case, I use my value of my f of I minus 1 and I need to transfer some of the elements from f of I minus 1 to f of I. Now, notice one thing. If I am transferring some elements from f of I minus 1 to f of I, I'm not going to reduce f of I to 0 because, well, it doesn't make any sense if you transfer from 4 to 1 and make it 3 and 2 and then once again reduce it to 0. Basically, you have transferred it over here and then you have once again deleted it. Rather than that, you could just delete it from over here. So I'm not going to make it into 0. So when I'm transferring, I'm sure that I need to make it into x. And the question is, how many elements can I take from f of I minus 1? Now, f of I minus 1 has two choices. Either it could go to 0 or it could go to x. All right. If it could go to 0, if f of I minus 1 goes to 0, in that case, I have f of I minus 1 elements that I could basically transfer forward. If it goes to x, well, there are again two conditions. If f of I minus 1 itself is less than x, so f of I minus 1 lies over here and x is over here, then I actually need to put in more elements to basically make f of I minus 1 go to x. So I can't transfer any new elements without having overheads. But if f of I minus 1 is greater than x, then I can have this portion, which I could basically take and transfer it to f of I. And so this would be what I do for these two elements. And what we can do is, and what I want to do is, okay, this is what I do for these two elements. And what is the answer of the remaining, the rest of the array. So in such situations, what we usually do is we maintain a DP array. Like why DP? Like our DP would basically tell me what is my minimum operations up to the ith element. So like what is the minimum operations I need to make I prefix I valid, like prefix I valid. So what my DP of I will tell is what are the minimum number of operations I need to make my prefix I valid. And what I can do is, for each of the I, what we can do is for each of the I, we have two conditions. We basically ignore the rest of the array and just try to make this I into X or 0. Or we have something, we consider I minus 1 and I, and try to make both of these equal to like 0 0 or uh, 0x, not 0 0. The second element would never like go into 0 0 in that case, but basically 0x or xx. And the rest of the array would be processed in way that, anyway, like the rest of the array would be processed in uh, some other way. Also, why wouldn't there be a connection from like over here and here? Like, why are we considering like there won't be any transfer from I minus 2 to I minus 1? Because as we saw above, when you have more than one transfers, like if you transfer from this element to the next element, you incur one cost. If you transfer from this element to this element, you incur one cost. And the moment you say that I am also going to transfer from this to this, and then once again I am transferring from this element to this element, you're incurring a cost of 2. And it basically says that there's an optimal solution where one of these is eliminated. And if one of these is eliminated, basically you could cut your array over here or over here and say that there won't be any transfer for this ith element. And yeah, like we could just have our dp of I equal to the minimum of whatever all the cases. Like for the ith element, we will have three cases. One is that there's no transfer, like we need dp of I minus 1 to make this prefix valid, and we'll need the minimum of like whatever the frequency of I is to convert it to 0, or x minus absolute value of frequency of I to convert it to basically x. Or what we can do is we can consider I minus 1 and I, and we need dp of I minus 2 to basically convert the remaining rest of the prefix into a valid subarray. And for I minus 1, we need to transfer some number of elements to I. And basically in that case, what we do is, okay, how much can I transfer? So the first thing is I can make into this guy into 0 and this into x. So in that case, we'll basically have like frequency of I minus and 1 elements would be transferred over here. So that would incur the f of I minus 1 operations. And then we just try to make f of I into x. So over f of I, you would have these many operations. Actually, the minimum of this or x. So if you have any more than that, you would just delete them. So, right, like those would be the transitions for your DP. Now, the time complexity for this would be you're first fixing the x. So x would go from 0 to n. That would lead to n iterations. Then for each iterations, you are iterating over an array of size 26 and maintaining basically all your DP array and calculating your DP array, which would once again be done in big of the size of array time. So which would be like big of n into 26, which would kind of be O of n because 26 is a multiplier. And for space complexity, that too would be big of 1 if you just consider DP array because that has a fixed size of 26. Now, I think, are there any? Okay. Now, like, if I were to just like visualize what's happening over here. So what's happening over here is this is your f of I minus 1. This is your f of I. And let's just say that this is your x. And we just say that f of I is like less than x. Now, f of I by itself has two choices. You could either insert these in many elements and fill this gap to make it equal to x, or you could remove these many elements and make it equal to 0. The other option that you have is you could have f of I minus 1 and transfer some elements from over there. So this is your x, and let's just say that your f of I minus 1 is over here and this is over here. You could take this chunk, you could remove it from over here with these many operations and basically transfer it to f of I, and then once again fill the remaining gap with like insertion operations, and that would once again that would basically allow you to make both of them equal to x. Or you could have one more scenario, a third scenario, where your f of I minus 1 is over here, your f of I is over here, and this is your f of I minus 1, it's less than x, and this is your, say, f of I. What you could do is you could just convert this whole f of I minus 1 into 0, transfer this whole thing at the top over here, let's just say it comes over here, and basically try to fill whatever gap remains. Also, one more thing that may happen is maybe your f of I minus 1, this is your x, and this is your f of I minus 1, and this is your f of I. Maybe you don't require the whole part of it, like maybe you require only this part, and this part will be enough to take your f of I to x. In that case, what you can do with the remaining part is, rather than transferring it over here, you could just delete it. We could just delete this part. All right. And yeah, and basically while doing this whole thing, we maintain our DP array, which basically tells me that what is the minimum number of operations that I need to make ith array and valid array. So this would be the code for the problem. First, we calculate our frequency array. So our frequency array has a size of 26 because we have at most 26 characters. Then we have the size of our string. We basically iterate over our complete string and calculate the like increment the frequency of each character. And initially, like at max, what you would do is delete all the characters. So at max, your answer would go to n, and then we try to fix our x value, that is what is the like my final array can have 0 or this element in it, and we try to calculate what is the minimum number of operations that I need to make my frequency into 0 or I array. And this is how we would do it. Like first we start with a DP array where DP of I says what is the minimum number of operations that I need to make my prefix valid, that is all elements 0 or x. For the first element, we don't have any previous element, so you either make the first element to 0, that will incur frequency of 0 operations, or you change it to x. Now if it's greater, then that would be frequency of 0 minus x. If it's lesser, then that would be 0 x minus frequency of 0. Overall, we consider the absolute value. Then for each of the next elements, what would happen is like the first thing is we don't really do anything with I minus 1. We don't have any operations of type 3 that involve I. In that case, we'll first convert or complete prefix I minus 1 to valid array, then change the ith element either to I or either to 0 with these many operations, or to x. Now the previous basically says that what is the minimum number of operations that I need to make my prefix up to I minus 2 valid, that is either 0 or x. Then then the rest of the rest of the code basically works only if my frequency of I is less than x. Well, why this condition? If you actually see, if my frequency of I is greater than x, so if I am here and if I'm transferring more elements over here, I'm actually only adding to my overhead, so it doesn't like make any sense. Rather than transferring them, it would be better to just delete them. So for this, what we do is, if my frequency is less than x, that is if I need to insert more elements to make the ith element a valid one and to make it up to x, then I have two conditions. If my frequency of I minus 1 is greater than equal to 0, well, if it's greater than equal to 0, then I can just cut it at x and get this extra portion and try to insert it in my x, like in my ith array. So this is the carry part. Like this is the amount of operations I will do to basically carry them over. Then my dp of I, like the number of operations I need to make the ith array valid, is whatever the previous, like whatever I need to make my prefix I minus 2 valid, plus I need to do carry number of operations to make frequency of I minus 1 equal to x. I either carry them over to I or I delete them. And we say over here like the maximum number of operations over here is, yeah, like basically like this is your if you carry over these guys, like once you if you have this x, this you have this x, and you have these like carry number of operations over here. Now this was your frequency of I, this is your carry, and how many operations do you need to fill this gap? Okay. Or you could, it may happen that the carry may exceed your x. In that case, rather than carrying over those elements, you just basically we just we just delete them over here rather than carrying them. So this basically says what is the minimum number of operations I need to fill the gap that is still remaining. Or the other case is that my frequency of I minus 1 is strictly less than x. In that case, rather than having to fill up to x, what I would do is I'd just reduce my frequency of I minus 1 all the way up to 0. To do that, we'll use carry number of operations, reduce it down to 0. Then what is the remaining gap? What is the gap that still remains even after a carry over all the redundant elements from the previous array, like the previous element? We have these many, like this is my size of the frequency of I after my carry, and this is x minus is the size of the remaining gap, and maximum 0 or that, because it may happen that it may exceed, and if it exceeds, then we just don't carry those many elements. Rather than that, we delete them from the previous element. And finally, like we just calculate the whole DP array. Then DP of 25 would basically denote what is the minimum number of operations I need to make all the 26 elements starting from 0 all the way up to 25 into like all the like the complete 26 elements into either 0 or x. And this would take 26 like 26 iterations of the for loop, and we basically try to fix our x to 0 to n. 0 would be you delete all the characters from the array, and would be like or the complete array has been converted to character of just one type, and we take the minimum of these things. And in an optimal scenario, like it won't go outside the 0 to n boundary. So that was the fourth question. And okay. About the So that was the fourth question. For the second question, like you could use many algorithms, and the one particular I use over here was Z1. So I'll just try to code up the rolling hashes solution. I'll also share that solution. And yeah, that was it. So uh, I hope you enjoyed the PCD. And if right. All right. So that was the last question, and that was